My name is Nick, and this is my physical science video over casting a fishing lure. I chose this activity because I already fished over the weekend, so it was easy to record these videos. To calculate all the equations we have learned all year, I will need to gather some basic measurements. First, I will need to find my distance. Now I need to time how long it takes for my lure to travel the given distance. Finally, I need to find the weight of the lure. I now have all the information I need to calculate the rest of the equations. When I cast, the lure travels about 25 meters. Distance is the measurement of the path followed from the starting point to the ending point, while displacement is the measurement of a straight line from start to finish. This is why my distance and displacement are the exact same, because I chose the lure not to return back to me. Velocity is a change of distance over time. I took the distance of 25 meters and divided it by the time it took to travel 25 meters, or 3 seconds, and ended up with a velocity of 8.33 meters per second. Momentum is the mass of an object times the velocity. I took the mass of the lure, or 0.014 kilograms, and multiplied it by the velocity, 8.33 meters per second, and got my momentum of 0.117 kilograms times meters per second. The momentum is small mostly because the weight of the lure is very small and can be stopped easily. Acceleration is the final velocity minus the initial velocity, divided by the final time minus initial time. Because my starting velocity and time are both 0, I just do my velocity divided by the time it took to cover 25 meters, or 3 seconds. Isaac Newton created the 3 laws of motion to explain all forms of motion. Newton's first law states that an object at rest will remain at rest, and an object in motion will remain in motion unless acted upon by an outside force. As you can see, the fishing lure is at rest, but once acted upon by an outside force, it is thrown out to the water. Newton's second law states that the force of an object is equal to the mass times the acceleration. Newton's third law states that for every action there is an equal and opposite reaction. As you can see, the lure is being pulled down to the earth, but the fishing line is applying an opposite force, pulling up. When I cast, it is an unbalanced force because the force I exert is greater than the force of the lure. This free body diagram represents all of the forces acting upon the fishing lure. Because the lure is in the air resistance pushes against the lure instead of frictional force. The applied force is when I cast the lure out to the water. The tension force is when the fishing line pulls against the lure while in flight. And the gravitational force is what pulls the frog down towards the earth. Friction is the amount of resistance an object encounters while in motion. After I cast, the lure flies through the air easily but is slowed down eventually because of air resistance. Once gravity pulls the lure all the way to the water, the lure stops in its tracks and it encounters a large amount of friction. Gravity is a force that pulls 2 objects together and is measured in newtons. As long as the object has mass, it is affected by gravity. My frog isn't that massive, so it has a very small gravitational force. Mass is the measurement of how much matter is in an object and is measured in grams or kilograms. The mass of my frog will not change, even if it is on the moon, Mars, or Pluto, basically anywhere in the universe. However, weight can change. If the mass of my frog is 0.014 kilograms on Earth, it would weigh 0.137 newtons. But on Mars, it would weigh 0.05 newtons. Work is force multiplied by distance. It takes little work to move this frog because the force of it is small. Power is force multiplied by velocity. The frog also has little power because the force is so small. Potential energy is when an object is at rest. You can calculate potential energy by multiplying the mass, gravity, and height. Kinetic energy is when an object is in motion. You can calculate kinetic energy by taking half of your mass and multiplying it to your velocity squared. As you can see in this video, when I'm holding the frog in my hand, my potential energy is 0.21 newtons. But when I drop it, my kinetic energy is 0.49 newtons. This project helped me see how you can apply physics to the real world. I realized that if you have the height, distance, time, and weight, you can figure out a plethora of equations like work, power, kinetic energy, potential energy, acceleration, and velocity.